Welcome in everyone to the AI reading group by Women in AI and Robotics. My name is Cleo Norris, and I'm a volunteer with the Montreal core team. And we're really excited to create a space for direct dialogue between researchers and the community to allow for deeper engagement with emerging research. So with that, I'm excited to introduce our speaker. Elon Du is a senior research scientist and incoming assistant professor at Harvard. He will be presenting the paper Improving Factuality and Reasoning in Language Models Through Multi-Agent Debate. So with that, I'm excited to welcome our speaker. This going here. And here we are. Elon, are you muted there?
Oh, hello, can you hear me?
Yes, perfect.
Awesome. Okay, great. Yeah, well, thank you so much for the introduction. And yeah, feel free to ask if there are any questions. So I'm going to share a bit on this paper, Improving Factuality and Reasoning in Language Models for Multi-Agent Debate. So the overall idea of debate is that normally when we have a question, for instance, there are 175 diamonds and 35 fewer rubies. How many gems are there in a chest? Normally, we just directly ask a single language model to generate the final output. The idea of multi-agent debate is that instead of having a single model generate the output, we will have multiple instances of the model or multiple different language models generate possible answers. So one model might say, let X be the number of rubies, and we find that X equals 40 gives us 3 times 40 plus 105 equals 225, which is incorrect. And in contrast, maybe a second agent will give us the correct answer, which will be if there are 175 diamonds, and it's 175 plus 140 plus 280, and it gets you the correct answer of 595. But the thing is, we don't actually know which language model is correct and which one's incorrect. So the idea of multi-agent debate is that we ask each agent to talk with each other. So now each agent will be prompted with a question using the solutions from other agents, give an updated response. And each agent will now give an updated answer to each of the questions given by each agent. And we repeat this procedure until we converge into a final answer. And the idea is by having each agent really look at each of the other responses from the other agents, as well as reason about their responses, the final answer you can get a much more accurate final answer. So let me give another example. So let's say I have a chess. So here I have an image of a chessboard, and I have the question, what is the best chess move I should execute? So initially, two models might give separate answers. One might say dxe6, and another one might say be3. And now you ask then the model gives the instruction, while using the responses from the other agents, give an updated response. So update your response given the responses of other agents. And now each agent will, because each agent has a different answer, now they will reflect on this. And then they would say something like, I would suggest the move QA4, or I would suggest the move BE3. And by repeatedly having each of these agents chat or like discuss or try to find an answer in response to what other agents say, we will continue to get better and better answers until we both hear that both of the agents converge to QA4. And in this case, we actually show the relative pawn advantage of each move. So we can see that over the course of the debate, these agents are able to get increasingly more accurate answers. So one way to think about multi-agent debate is that it's a type of inference time scaling algorithm for reasoning that combines the best of a couple different methods. So one idea is multi-agent debate is similar in the sense to consistency, self-consistency or majority voting, where you generate many different answers. Because in multi-agent debate, we also generate many different answers, although the answers are from different language models. But the difference is in consistency, we choose the most common one and use that to find the best answer. Well, in multi-agent debate, we actually ask each agent to chat with each other and use that final response to get the correct answer. Multi-agent debate is also a little similar to self-reflection. So in self-reflection, usually the model is asked to reflect on its answers and use its previous answers to improve its final answer. And in multi-agent debate, we have something similar where an agent reflects on the answers of every single model, not only the first one, and use all those responses in tandem to get the final prediction. So essentially, multi-agent debate is kind of you could imagine it's like the mixture of these two approaches, where now you have many agents and all the agents reflect on the responses of other agents, and this combination generates the final response. So let me just illustrate this again. So imagine we have four responses. So we have LLM1, LLM2, LLM3, LLM4, and these can be very different. These couldn't be the same LLM, where we can just assume that due to random chance, each response will be different. Or they could be different LLMs. And you could also imagine you have something in between, where each of these LLMs are the same LLM, but you prompt it with a different prefix. So maybe on one of them you say pretend you're a student, another one you say pretend you're a teacher or a professor or so forth. So now once you have this first round where each of these four LLMs generate different responses, what you do is let's say LLM2 wants to generate a response. What it does is now it takes the responses of every single other LLM and combines them together to get a new response. And you have something similar for LLM3 and LLM4, and then LLM1 also. And this gets you an updated round of responses. And then once you have this, now you do the same thing here, where again, each agent sees the response of all the other agents, and just repeat this procedure. And yeah, and then basically, the overall goal of this approach is that this allows each agent to critique or assess the factuality or the logicalness or reasoning of each response in light of the other responses from other agents. Okay, cool. So let me show a concrete example of what happens here. So now let's consider this like relatively simple grade school math problem. So we have the question where you have Romeo boards a train with 120 people. At the first stop, 20 more people board the train. At the second stop, 50 people descended the train, while twice the number boarded the train. And if 80 more people descended at the third station, you want to calculate the total number of stops. And then what you can do is you can just directly try to do this. So you have 120 people, you add 20, which is 140. And then you say, and now this model does the incorrect reasoning, but it says at the second stop, a total of 50 divided by 2 more people boarded the train than those that left, which gives you 25 people. And then they subtract, but the second step is wrong. And in contrast, this agent actually does the right computation. So it says, well, okay, there are 120 people, I add 20 more people. Now, if the 50 people descended, but twice that many boarded, well, then we do this, and then we subtract 80. So now we get the correct answer of 110. So you can see that one response is correct and one response is incorrect. But the interesting thing with debate is now you give the model as instructions the responses of other agents. And then you say, is using the solutions from other agents additional information, can you give an updated response? And now you get an updated response here. So essentially, by using the fact that you see the responses of other agents, you can more accurately critique or think about your reasoning chain so that you can get a better final answer. So here's another example. So this one is interesting because we have this multiplication problem here where we want to compute 23 plus 19 times 22 plus 22 minus 7 times 9. So this is a somewhat complex computation. And because it's a somewhat complex computation, and we also ran these experiments around 2 years ago, I think some of the models nowadays are a bit better at arithmetic. What we find is that each of the models messes up in their own way. So here, here I think there's some error in the arithmetic, and then here again, there's also some type of error with the parsing. But what's interesting is both agents get it wrong. But because both agents, when you prompt, let's say agent one, and you say use the solutions from the other agent as additional information, the interesting thing is that because it's wrong, but it's also examining the other wrong answer from the other agent, and it's trying to see where the first agent is wrong and where the second agent is wrong. So because there's this self-reflection procedure where you're trying to locally see what is wrong in each solution, the agent's actually able to stitch together the correct parts of the first response and the correct parts of the second response to get a final correct answer. And in a similar way, the second agent is able to stitch together the correct parts of the second response with the correct parts of the first response and get the final answer. So essentially, this debate procedure can allow you to be accurate even when all your initial answers are incorrect. So here's some more examples of this. So here are a couple more arithmetic expressions where here we don't actually show the entire response. But you can see at the beginning all the agents are wrong, and over time you get more correct answers, or like sometimes they're all wrong and then one gets correct and then two gets correct. So there's an interesting dynamic as these agents communicate with each other. And outside of just doing reasoning, this is also, you can also use this to do factuality. So here you ask one agent to list out the correct information about one person, and you have a second agent list out the correct answers on the second agent. A second agent lists out the correct facts about the same person. And what we find is that for responses that are shared between most of these responses, they're amplified. While the things that are different, so what we found with a lot of these models was that for responses where the model was not certain about the final answer, it would often generate multiple different answers. Um, and when you have multiple different answers, what the models, since the models can see as context the other agents' responses, it can see that these answers are inaccurate or inconsistent. So by doing this debate procedure, now these agents are able to get a set of answers that are much more accurate. So this procedure isn't just useful for reasoning, but also for isolating facts that the language model is confident in. And here are a couple more examples. Here you have a couple of math questions, and again, originally the answers get the incorrect answer, and now after the debate, they're able to get the correct answer. And so overall, what we find is across a wide variety of domains we investigated, ranging from biographies, MMLU facts, or chess move optimality, arithmetic, grade school math, or chess move optimality. What we find is that this type of debate procedure generally improves the performance compared to the single agent baseline. And keep in mind, we did a lot of these experiments in roughly 2 years ago. So at that time, only GPT-3 was available, GPT 3.5. Nowadays, there are a lot of different language models. So I think a lot of these results could be much better if we consider using multiple different language models as opposed to a single one. So another interesting thing we find, uh, yes, okay, there's a question. So the question is, how does the model know that the answer of the other model is correct if it itself just produced an incorrect answer? And how often does it know that what constitutes a correct answer versus not? So what we find is, yeah, in practice, since the models don't know the ground truth answer, there's no way for them to know if their answer is incorrect and the other model's answer is correct. But what this procedure does is it encourages the model to pay attention to both its response and the other response. And by paying attention to both of these, there's a greater chance than not that the model can realize that one answer makes more sense and it gets the final next answer. But it's definitely the case that there are settings where the model is actually correct and the other model is incorrect. And then after conversing and seeing the other model's answers, first model actually changes and does the incorrect answer. So that happens a lot. And what we find is this is also really dependent on the reasoning ability of a language model. So what we find is that for these very small models, like maybe 7B or a smaller scale, when we do this type of reasoning, um, it turns out that the models do not work very well because they can't really reflect on the responses of other agents. But we find that for these much larger models like Gemini or GPT, now the model performance is much better because the models can more effectively reflect. Great. Okay, so yeah, thanks for the question, and feel free to ask other questions if you have any. So let me go back to this slide here. So in the previous procedure, I talked a bit about this multi-agent debate procedure where we have a number of agents, they generate responses, and now each of the agents respond to the other response, critique or update the responses in light of the responses of other agents. So as a result, this debate procedure, you can just gradually increase the number of agents. So you can go from one agent to two agents to three agents, all the way to seven agents. So you can simply just, when doing this debate procedure, you just use all seven agents. There's a bit of, so what we find is first, as we increase the number of agents, the performance gradually goes up. The interesting thing is, as you increase the number of agents, what happens is you concatenate the responses of all the other agents as additional context for updating the response of let's say, the seventh agent. And it turns out that as you have more agents, this context gets increasingly long. And at the time we were running experiments 2 years ago, as the context got longer, the performance of the models dropped a lot. So what we do for a larger number of agents is we actually summarize the responses of all the other agents. We don't actually just correctly concatenate them because that reduces the context a lot. But like with these larger models with potentially longer context size, this might work much better in the future. Another thing we tried is just trying to increase the rounds of debate. So if we just have one round of debate, we just generate from each model and we just do a majority vote. With two rounds, the models reflect once, and then you do the majority vote. With three rounds, you do one more time, and then four rounds, you do a time after that. And what we find is, so this is for arithmetic, but what we find is in general, as we increase the debate rounds from 2 to 3, there's a relatively decent large boost. Was I think the biggest boost from 2 rounds. 3 rounds has a slightly more marginal boost, and then 4 rounds is fairly similar to 3. Our thought is that usually by the third or fourth round, the models have mostly fully converged. We were trying to experiment on, I guess, roughly relatively simple math problems. So as a result, I think that probably 2 or 3 rounds was sufficient. It may be that for much more complex problems, additional rounds of debate could further improve performance. And then another interesting thing about debate is this idea of debating between different models. So when we were running these experiments, the only models were ChatGPT and Bard. But when we tried this interesting experiment where we had this question, math question, and we found a setting where ChatGPT was incorrect, and Bard was also incorrect. But they were incorrect for different reasons. I think Bard was incorrect because it did the arithmetic incorrectly, and ChatGPT was wrong because it parsed the question incorrectly. But with this debate procedure, you can now copy the correct mathematical parsing from the second model with the reasoning of the first model, and now you can get an overall correct answer. So essentially, this debate procedure can be seen as a way to really combine the strengths across many different language models. And in general, this type of prompting is pretty synergistic with other forms of prompting. So you can also do zero-shot chain of thought prompting, where you ask the model to think a bit more before doing the reasoning. And we find that as you add the chain of thought, well, you get a relative boost in performance with debate. And one side comment is nowadays there's a lot of work on these reasoning models. And you could also imagine that you could do this debate procedure with reasoning. So you could have some type of reasoning to generate the initial responses, and then you can have more reasoning to really critique and understand the responses of other agents. So that's another interesting direction to go. One other interesting thing we found was that we could control the efficacy of debate by changing the prompt that we used. So if we made a prompt where we really encouraged the agents to immediately converge to the correct answer, what we found is that this led to a larger boost to performance at the beginning, but your final performance after many rounds of debate was actually not that much high. It was fairly low. But if you have some type of prompt where you encourage the models to spend a bit more time talking with each other, so as an example, a prompt that would encourage models to immediately get the answer could be, give your final answer, or like, what is the correct answer? Well, or like really have high confidence in your answer. Something that induces a longer form debate could be these responses are responses from other agents that may not be very trustworthy. Based off this, update response. So you reduce the confidence of the models in the responses of the other agents. But what we find is that doing that allows you to have more rounds of debate and to have more consistent performance gain after each round of debate. And a final thing that's interesting about the debate procedure is that we went and evaluated the perplexity of the final responses as we ran the rounds of debate. And what we found is that the perplexity or the confidence of a language model in its final response seemed to get increasingly lower. So that means that the models are increasingly more confident about the response. So one way to think about debate, especially if it's multiple instances of the same language model, is essentially you're doing some type of search to find a set of responses that the language model is most confident in. And essentially this type of having multiple different threads of thought and then like trying to mix them is a way to do this search procedure to find these highly confident responses. Great. So that was a quick overview about the multi-agent debate paper. I'll also talk briefly a bit about our follow-up to this multi-agent debate paper, where now we actually try to fine-tune and specialize multi-agent debate models. So here's another illustration of the debate procedure. So essentially, you have an input, you have n different models. Each model generates initial responses. And now for each model to generate a new set of responses, it will summarize the responses from the other agents as well as an old response, and then make a new answer. And you repeat this many rounds until you use majority voting to get the final answer. So the idea of this follow-up paper on multi-agent debate is that instead of it's really beneficial when doing this debate procedure, when combining all these models, to try to make the models specialized or different in their own way. And the idea is if model one is different than model two, which is different than model n, well, each of these will come up with different ideas to solve a problem. And then each of these models will then come up with different ways to refine your solution. So by making each of these models more distinct, we can explore a bigger space of solutions and use that to get better answers. So in that line, to get a set of n models that are different, what we do is we take each of these models and we essentially fine tune each model on the answers where each agent is correct on. So model one, so we first take these models which are initially initialized to the same set of weights. We take their responses. And then we just choose the responses of model one that are ultimately correct with the final answer. And the idea is because each of the, although the models initially are identical, because you are randomly sampling some solutions from each model, the models by random chance in the end of the day specialize and learn different aspects of the problem distribution. So that's the overall idea for fine-tuning the generation model. And we do something similar for fine-tuning each critic model, where for each critic model, we fine-tune the critic model on the answers where the critic was correct. So the critic model at the end of the day gave the correct final answer. And what we do is we fine-tune, let's say we take the first critic agent, well, we tune it on some portion of data where the answer from the previous, from model one was correct. And then the critic gave the final answer afterwards. And we also train it with some proportion of data where model one was incorrect, and then the critic makes the answer correct. And we do this analogously for all of these critic models. So now we get a set of n specialized critic models, where each one is a little different for critiquing or updating the response. And what we find is that this type of procedure, where we're not specializing or fine-tuning a single model for reasoning, but rather we're now doing this fine-tuning procedure across a set of generation and critic models. What we find is that this actually gives you a pretty nice boost in performance over multiple rounds of fine-tuning. So we find that if you do single agent like fine-tuning, where you take a agent, you generate a bunch of responses, and you just fine-tune the model on the correct responses, what we find is that improves performance over one iteration and two iterations. But as you run more iterations, because the diversity of the responses decreases over time, you start seeing this issue where things start dropping over time. But if we do this more multi-agent fine-tuning, what we find is now after each round of fine-tuning, the accuracy consistently goes up. And we find this across a set of different models. And one way to understand this is this idea of diversity in thought. So in general, we want to the overall goal of multi-agent debate is to have different agents have many different thought processes and to use this critique procedure to essentially find the correct diverse thought process that gets you the final answer. And what we find is that by fine-tuning each of these models on specialized data, if we look at the diversity of responses generated by this population of agents, as we run through the iterations of the fine-tuning, this diversity gradually increases, as seen here. But now if we simply just fine-tune a single language model, so we just iteratively try to make that model copy the correct answers it generated in the previous iteration, then we find that diversity actually drops over time. So one idea is by fine-tuning in multi-agent debate, by fine-tuning models to be more specialized with respect to each aspect, what we find is there's a much more consistent improvement in accuracy. Okay, great. These I think are more filler slides. But yeah, I think this is overall the summary of the paper. I'm happy to take any questions now. And thanks everyone for listening.
Thank you so much, Yelin. I'll remove the pin and we can see it in gallery view. That was really fascinating, and I think also the follow-up was it was great to see that there were kind of future directions that came out of this original paper that we were talking about. But yeah, I'll invite the audience here on Zoom and also the audience on Hugging Face to send your questions into the chat, and I'll get them and we can ask them. I can start us off. In the original paper, and you kind of touched on this in the next paper with kind of diversity of thought, but in the original paper, you compared the debate process with other methods of improving reasoning.
Mhm.
Oh, sorry, this is a different question. We'll get to the other one. So what are the key mechanisms in the multi-agent framework that led to improved factuality and reasoning? So there were a couple things like diversity of initial responses, the rounds of debate, consensus mechanisms, all that kind of stuff.
Mhm.
So what were the
Oh,
key ones that
what were the key rounds? Well, I think it's mostly probably a combination of the fact that you have multiple different agents, and
mhm.
we're pooling between the agents. And I guess we're pooling through the or we're pooling the responses of all the agents, but we're pooling them in a way that's a little similar to like self-refinement because you're now looking at all the responses of other agents in combination to generate your final response. So I think
Right.
the fact that we're combining a couple of reasoning strategies from multiple samples to this reasoning, to this like self-reflection or like self-critique, I think that combination seems to have helped performance quite a bit.
Okay. That yeah, that makes total sense. And we have a question from an audience member here. So does this model only work with arithmetic questions?
No, so we do it on quite a few quite a few different other settings. So we also do it with like GSM. I think we do it on the math data set also,
Mhm.
especially in this follow-up paper, this multi-agent fine-tuning. I think we try it on a bunch of different reasoning tasks. Uh, so yeah, in general, it's a pretty general approach. I think there's been a couple of works that have followed up on this approach also. So people have used it for much more open-ended dialogue generation, as well as for like evaluation of like even model evaluation. So I think there are a lot of things you can use this multi-agent debate procedure on to help performance.
That's very interesting. And I actually had a similar question in terms of like how does this approach handle questions that are subjective or inherently ambiguous? Like, are there risks of oversimplification or reinforcing majority bias, that kind of thing?
Yeah, so that I think that's a pretty interesting thing to think about. So I think it is definitely the case. So when you have an ambiguous problem at the very beginning, every single I guess each model will have different responses. So if it's an ambiguous problem, maybe some of the models will have the one interpretation, and then other models will have the second interpretation. But then because we do this this approach where each model sees the response of all the other models. Over time, like the perspectives of each model does do kind of change in the sense that they look at all the responses. So it may be the case that if in the sampled population, three of the models or four of the models have one view and one model has another view, then probably over time, most of the models will actually converge to the first view. So I think there is a effect of like a population like bias where like over time the models seem to be very where the models might like just converge to the common group answer. And I think there's some interesting things to think about on how you can avoid this. So you could potentially try to actually change the way the models communicate. Maybe you want to actually do some prioritized sampling where you group the models by answer and then you keep a population of models as different answers. But I think there are interesting mechanisms you could do to try to prevent this.
That's really interesting in terms of grouping and would those models kind of be trained in or, pre-prompted in different ways that would might make them come to a different consensus answer? Like, for example, different perspectives in the prompt
Yeah, I
intent.
think that would be interesting also. Yeah, so you could imagine also prompting or changing the model
Yeah,
do.
interesting. Okay, cool. And we have another audience question. So how is the confidence of the model calculated?
Yeah, so we don't have any implicit way to really to evaluate the confidence of the model. So each model, I guess we look at how much the model is willing to change its responses given the responses of other models. So I guess that is inherent. That is like kind of a way to tell how confident the model is, but we don't really have an explicit way to really do that. Um, I mean, it would be interesting. One thing we tried early on is once you have the final set of responses from the model. You could also prompt the model and ask them, how confident are you on the responses? And then you can try to use some type of confidence weighting based off that. We didn't find too many gains at the time, but we also didn't investigate this too much. But right at the current moment, our approach doesn't actually use the actual confidence of the model. Or the only way you really use it is based off how willing each model is able to like change their response to
Yeah.
given the response of other models.
Yeah, that's a good point. And again, if people have follow-up questions, feel free to send them in the chat and same with the from Hugging Face. Okay, so you touched on this in the paper, but given the computational cost of multi-agent debate, do you see this method as practical for real-time applications? Or like where would the trade-off be worth it?
Yeah, I think right now there's been a lot of interest in like inference time compute or like test time
Mhm.
scaling. So I view this like multi-agent debate as a very sophisticated way to do a lot of test time compute or to get more creative answers, especially if you try to make the models more specialized. So in that sense, I feel that this is very useful for settings like in scientific discovery where we want to do new ideas, or maybe when we have like questions of like maybe societal issues, or like we want to like figure out what is reasonable, like what is a good judgment or not, where there's a lot of ambiguity in the final response, and where it's not so important that the responses are immediately given to you.
Mhm.
So I think I view this as more of an approach for like much more like test time scaling. I guess one thing that is interesting though is that once you have this approach, you could imagine that yes, this is a bit slow. You use this to generate a bunch of data, but then you can just fine tune and distill the model to generate quickly from this data. So in that sense, this approach actually is can be a pretty useful self-improvement loop for getting faster generations. But this approach by itself, I think I see as more of a way to get like much more open-ended responses.
Yeah, that's really interesting. And I agree kind of with the open-ended in terms of like there might be a consensus, but it might be a subjective subject, so it's not the only answer.
Yeah.
And then kind of what you just said about maybe you're not in a rush to get the exact answer right away kind of struck me because do you think there would be any value in actually witnessing the debate happening? So kind of seeing what sort of way you could think about a problem, like different ways to think about a problem, is that valuable too for scientific discovery, for example?
Yeah, I think so. So I think one really nice approach or a nice thing about this type of reasoning with models is that
Mhm.
it's very interpretable. So you can actually see the entire transcript between models.
Yeah.
And so even let's say if the models were really, really powerful, even if you can't understand exactly what the models are doing, hopefully if they are faithful to the text they generate,
Mhm.
then you can still tell the internal mechanism of reasoning the models. And I think there's a decent amount of work in the AI safety literature where people are using some type of debate to exactly like try to understand the inner workings of the model, or like use this as a way to like audit or like reliably like determine how trustworthy a model is.
That's very interesting. So yeah, lots of applications, especially in sectors like financial sector where you really need to understand why it made that decision. So another audience question, what would be the minimal hardware required for this multi-agent debate approach using only small models like the three you showed in the slides?
Yeah, so I think then hopefully the hardware requirements shouldn't be too much. So I think you can probably do it with like a normal like A100 or a 2080 probably. I think that like with these small models, like you can do this with 7B models or like I guess 3B models. It depends a bit on actually the quality of the model as opposed to the actual size. Like something like Phi or Quinn 1.5B probably is already working with debate. But for those models, especially if you do some quantization, you should be able to run all three of these models together on the GPU. So yeah, so I think this should be pretty affordable, like in the sense that if you can load one language model, on one hand, debate can be instantiated using a single language model, in which case that's all you need. But then if you want to load a couple more models, you can also do that because the GPU resource utilization shouldn't be too high for these small models.
Okay, amazing. Yeah, and again, feel free to add follow-up. Um, so a question from the Hugging Face viewers. Um, let's see. Uh, from I'm not sure if this is a typo, but from the ablation, the reflection seemed to outperform the majority voting slash self-consistency. But I do remember a paper from DeepMind LLM um, that said that cannot self-correct reasoning yet. Saying reflection without external feedback does not work. Do you agree with this?
So I think there are so many papers in LLMs, and it's a little hard to know, right? So everyone has their own beliefs. I think that the way I view these papers is they talk about in particular domains. It seems like maybe the models are not able to self-reflect accurately. But my feeling is that depending on the domain and depending on the setting and like the models you use, there are times when the models can self-reflect, and there's times when they cannot. I think it is probably the case that the models aren't that great at self-reflection at the moment. And I think that's also maybe a limiter for debates. So we find that debate seems to help performance a decent amount, but maybe it's not like it would be awesome if you could go from 50%, let's say, to like 90%. And I don't think you see that gain as debate. And I think partially that's because the models aren't able to reflect that well on top of each other. So I think that like it suggests that like there's more room to go to improve this performance. Um, but at the same time, I do think that like depending on the setting, like there are definitely settings where reflection is working at the moment with even without external verifiers.
And what are some of those settings? Do you know?
I mean, even on these reasoning settings, I
Hmm.
mean, like they're also there. I think there are a lot more papers on doing self-reflection than there
Hmm.
are on like saying it doesn't work. But like I think
Hmm.
even for like I guess the settings the DeepMind paper showed, like it's not clear if it's definitely the case. I think they tried it on only a couple models,
Hmm.
and maybe they didn't spend that much time prompting, like tuning the hyperparameters. It's not clear.
Yeah. Okay, interesting. So another future area of research. Um, okay, and then this is a bit of a off to the side question, but in the paper you created a benchmark data set, right? To I don't know, benchmark the methods you employed. Um, so why did you and the other authors decide to create this? And do you think that domain specific factuality benchmarks are the way forward?
Yeah, so I think at the time when we created this benchmark, so we wrote this paper around 2 years ago when I think GPT models just came out. There weren't really factuality benchmarks at the time, or there were very few. So that's why we decided to construct our own.
Mm-hmm.
I think like if for more like applied settings where like you really care about factuality in a particular domain, I do think you want to just construct your benchmark for that domain because I think all the domains are very different from each other.
Right.
Um, Right, yeah, but yeah, I think the main reason why we did our domain at the time was because there just weren't many domains
Yeah,
overall.
absolutely. Okay, well, I think so on my end, those were the pre-prepared questions. I want to invite the audience for any last questions um, for Elon, but we can also try to forward any remaining ones if none come to the top of your head right now. Um, so yeah, but if no questions come in the next minute or two, we can start wrapping up. This was amazing to hear about the work and also the future work that's come out of this. And I guess one other question that I love to ask is kind of where is this going? And do you see more directions coming out of this?
Yeah, I mean, overall, I'm really inspired by this idea that, like, if we look at our brains, like, even when you're making thoughts, a lot of the times you have like multiple lines of thinking. So, like, you like when you're doing something, you always have like an inner monologue between like different voices and so forth. So, I feel that this type of this paper points to this broader idea that like we do decision making not by having one centralized giant neural network, but rather by
Mhm.
having a bunch of different models cooperating with each other. So, right now in this paper, we're combining different language models together. We have works on combining like having some language models be verifiers, other ones being generators. And we also have work on combining video models and language models and action models, or like combining multiple action models or video models. But very much, I think that the path forward to like the intelligent decision making might be this idea of having some type of the decentralized dialogue between many different autonomous models in charge of every single small computation. So I think this paper is kind of towards this direction of this more like compositional view of intelligence.
Wow, that's incredible. That's truly amazing, and I really hope that the members of our audience got a lot out of that too, and are kind of inspired to look at those connections because, yeah, I think that's very cool. It is very inspiring to kind of um, take things that we take for granted, for example, our own thought processes, and then see it work in technology. So that's incredible. So I'm not getting any questions now. Again, you can reach out to me or on Hugging Face, put it in the reading group chat or on Zoom. Please reach out to Women in AI and Robotics. But yes, thank you so much for joining, everyone. Thank you, Yulin, for an amazing presentation. And all the best at DeepMind and Harvard as you go into your um, teaching position. And everyone else, please keep an eye out for the reading group session in May. We'll be announcing it soon.
Great.
So
Okay.
yeah, thank you
Thanks so much.
everyone.
Yeah.
All right, have a good one.
Thanks, you too.
All right, bye.